I'll be notified as we go through here. My name is Jeff Slapp, as you know, and I'm the Director of Systems Engineering for the Americas here at DataCore. Just a brief background of my journey in my career to DataCore. I've actually been working for DataCore for about 2 years now, but prior to that, I had worked with DataCore all the way back as early as 2004, and I had started a consulting firm, professional services practice around that time, focused primarily on Vmware. And we found very quickly that we needed to have a storage system that was going to be robust but also affordable in order to take advantage of some of these advanced features with Vmware. So we actually started our company down here in South Florida. So interestingly enough, we found DataCore right in our backyard. And at that point, that really changed the entire direction of our company. So we primarily focused on Vmware and DataCore end-to-end virtualization solutions for clients all over the world, and did very well. Back in 2009, my company was acquired by a service provider down here. So after about 5 years of doing that, we were acquired and came on board, and we're asked by the acquiring company to essentially do what we've been doing for everybody else around the world. And that was deploying enterprise-grade, mission-critical, high-performance enterprise systems, both based on, of course, Vmware at the time and DataCore. And of course, this was a service provider, so this very quickly evolved into a cloud discussion, because that was around the time when things were getting very heated around that particular industry. And after about 5 years of doing that, driving that initiative, I decided to come on board with DataCore full time and be kind of at the tip of the spear, so to speak, driving the next generation storage platforms with DataCore. And it's been an amazing adventure, and certainly the last couple of years in the industry has sparked a lot of interest with regards to software-defined storage. And I'll talk a little bit about what that really means from DataCore's perspective, because there's a lot of, just like with cloud, there was a lot of confusion, a lot of various definitions out there with regards to how cloud was defined. In software-defined storage and storage virtualization and storage hypervisors, they all kind of fall into that confusion category where it's like, what do you mean by that? What do you mean by converged and hyperconverged and all of these different things? So we'll cover that today. We also, of course, are going to cover, from the technical aspect, the principal features of DataCore and how we're very, very special in the industry. And like I said, if there's any questions throughout this presentation, please ask. So I have this the technical deck, which is what we're going to start with. It's about 122 slides. All the material, by the way, that we're going to cover today will be available for download, and we're certainly not going to be able to cover all 122 slides here. I've actually presented this in its entirety before. It takes about 4 hours with one breath, so it's quite challenging to go through all of it. So we're going to focus on the core ecosystem of DataCore, where we live, what we do, why we do what we do, some of the nuts and bolts around how that's achieved, and then maybe if we have time, go into a discussion of what we call parallel I/O, which is really the nature of how we achieve the performance that we do, the world record-breaking performance, and we'll talk about some of the details around that. So let's go ahead and get started into the technical deck and set the stage for how DataCore does what it does with storage. So there's actually quite a bit here on the main title page, interestingly enough. So I'll spend a minute or so here. As you can see here, DataCore Software, we're a software company, and that's a very interesting space to be in, because today, as we know in the industry, there's lots of various hardware options, but it's all very, very common amongst the various hardware options that are out there. What really distinguishes solutions today is really around the software and the features that the software brings to bear on that very advanced, high-powered hardware that we have available everywhere today in the industry. So DataCore is a 17 years, soon to be 18-year-old company. Started in 1998. I think, in fact, we were about 1 month behind Vmware when they started, so very mature company. And of course, the story over the years has changed considerably. When people say, well, what does DataCore do? Well, we talk about storage virtualization, those sorts of things. And of course, today, it's a much easier conversation to have because we can relate that to other things that we work with in our day-to-day IT lives. And when we say, hey, well, we do for storage what VMware does for, for compute, that message is very quickly understood. But 17, 18 years ago, you couldn't have that conversation, right? If you said what we do for storage, what VMware does for compute, they would be like, well, what's VMware? What do you mean? Explain that to me. So that conversation, of course, has become much, much easier as the industry has evolved into this virtualization arena. So, 17 years ago, 18 years ago, the founders of this company set out to really make a quantum leap in the way storage was viewed in the enterprise. In fact, our CEO, George Teixeira, at the time was quoted saying that the future would be a software-driven architecture. Well, he was pretty close, right? Today we call it software-defined, but you could see where he was going with that. So now, after 17 years of development, we now have a 10th generation product, 12,000 plus customers worldwide with over 30,000 deployments in every vertical that's out there, every type of scenario imaginable, including even mission critical and life critical services. So very, very powerful set of capabilities, and also important to note, and I'll touch on this again later as we go through some of the features, it's a single product. It's not 20 different pieces that come together to form a solution. It's not widgets per se. It's an entire enterprise data services stack that drives I/O for your storage and for your applications. So let's go ahead and go into a couple architectural. I'm going to skip over this slide. I guess we'll touch on the feature set just to kind of level set with everybody, just to kind of give you the idea of what when we talk about features, what we're talking about. So the interesting thing here, besides the individual feature details that we can go into a little bit later, is that all the features that you see here, and most notably the most recent one down at the bottom there, the VMware Vball support, which just went GA on Tuesday with our PSP4 release, our version 10 PSP4 release. This now sets in motion the idea of now applying all these enterprise storage features across whatever the customer's storage environment looks like. So if it's a greenfield, obviously any storage in that space, of course, adopts the storage features that you see here. If there's an integration opportunity where, or a migration opportunity where something has to coexist with existing storage while they transition to the new platform or a new set of technologies in the environment, this allows, of course, the integration and the migration very, very simply all across a common set of front-end enterprise storage features. So one other thing I want to point out here is, while all of these features, of course, hopefully are names that you've seen and certainly recognize, there's two major things I want to actually point out. One is, while individually each one has an impact on availability, performance, efficiency, management, and so on, as you can see, they all have something in common together, and that is maximizing the hardware that we're running on to give you the most bang for the buck possible, and ultimately affecting the bottom line, right? Doing more with less, right? We say it a lot of different ways, but that's very, very important, because efficiency is very key to what we do in this space, especially now as we enter into a world where we're talking about with customers on a daily basis. Petabytes of storage now is becoming very common conversation, which is an amazing thing. If we think back to not that long ago when a terabyte was a tremendous amount of storage. Now petabytes are becoming kind of commonplace, and now we're talking about storage systems on the order of tens or even hundreds of petabytes. And of course that will continue. In fact, I believe it's accelerating the consumption of capacity. So we have to have a very, very efficient, very high performance, very highly reliable system to deal with that problem, not only today, but certainly in the future and well past that. So the other thing I want to also point out here is that while some of these names appear to be common with regards to, say, other solutions in the industry, I want to really stress that the name, of course, doesn't really do justice to what the feature does. So I'll give you an example. Auto-tiering, very common feature now, certainly available in most enterprise storage systems today. But it's really the mechanics and the methods in which it is implemented that really sets it apart. So the full name for auto-tiering, to give you just one example, is fully automated, sub-LUN, real-time, read and write aware, heterogeneous auto-tiering. Now, obviously, you can see why we couldn't put all that in there, but that is a full definition of auto-tiering. So don't assume that just because there's auto-tiering, if you have to go to battle against another solution, or if you're considering another solution, really pull back the covers and find out what's going on in the engine, how it's being done, and what the implications that's going to have in the environment, because that's going to be very, very important, especially at scale, right? So again, I'm not going to go through every single one of these in super detail, but I wanted to put this up so everyone had a good idea of what we were talking about when we talk about DataCore features. So now let's move into architecture, because this is extremely important to make sure that we're all on the same page with this. And I think you're going to find this is actually very, very elegant, very, very simple. We like simple here at DataCore. We always strive to keep things simple, and especially when we talk about some of the user interface features, the way it's been laid out, the simplicity, and what we've done is try to strive to keep the number of mouse clicks, if you will, to a minimum to do what would normally be very, very tedious storage tasks. So simple is good, and I'm actually going to skip over this one to go to the overall architecture diagram, which is right here. There we go. So I'm going to let this phase in here. Okay. So we're going to talk about three principal designs or deployment models, if you will. Now, again, you're going to hear me say this several times throughout this presentation, in that, and I'll say it once now to level set, DataCore is software. It is a single package deployed in various ways, and three of them are on the screen here. We'll go through them in detail. But regardless of how it's deployed, regardless of how many is deployed, it's all the same software. It's all the same engine. Whether you're talking about 2 nodes or 20,000 nodes, it's all managed from one pane of glass. Okay, so that's very important. So all those features that we just touched on also is equally applicable here, right? It's uniform across whatever storage we're controlling, whatever technology, whether it be PCIe-based, whether it be RAID-attached storage, external arrays. It doesn't matter where the storage is coming from. We're going to be able to apply all those features to that storage. Now, as a storage engineer, I tend to start at the bottom, so hopefully I'm not offending any of the network guys. We'll get to the network side in a moment. But I work my way up because, remember now, DataCore, the name was very aptly chosen because data is the most important component of your data center. I think most people would agree with that. We have a tremendous amount of infrastructure that exists in enterprise data centers today. Redundant switches, redundant channels, servers, uplinks, you name it, right? Everything's redundant. But then what you find, if you really are honest and you go all the way down to the storage, what you typically find in most enterprises is that you have a single copy of data, operational copy of data. I'm not talking about backups. I'm talking about online, real, accessible data. And it's interesting when you look at the fact that, well, okay, what would happen if that data went away, even for a moment? Well, then really at that moment, there's no need for the rest of the infrastructure sitting above it. All the millions of dollars and all the complexity that sits above the storage is all there to serve to access that data, whether it be reading and writing. So the data, it really gives purpose to everything else above it. So it's very, very important to, of course, have accessibility to the data. So that's, of course, why we named our company 17 years ago DataCore, because data is at our core. And it sounds a little funny, but that's really how we approach our view of data and storage and the technologies that are involved in that. So what we're going to do is we're going to start here at the ground floor, and we're going to start at the bottom, right here in the middle, right where you see the two largest DataCore red boxes there in the middle. We're going to start, first off, by talking about disk pools. Now, even before I get into disk pools, let's also make sure that everyone's aware. We are software, again, that's already been clearly defined, but we are software that runs on x86 powered hardware. Now that actually is also something that's fairly common today. It may not look like a server, but really when you pull back and look at the engine of most storage systems today, they're really just processor, RAM, and some channel capability. And that's really what we're doing here. But now we're able to now harness the power of any of the classes of x86, and I say that because that's extremely important. Lenovo has in its arsenal not only E5 Intel-based processor architectures, but also E7, okay? That is very, very unique because from a storage perspective, from a storage engine perspective, there is not a storage provider that I am aware of, at least, and I may be corrected on this, but in all my research, I have not found a single enterprise storage provider that is deploying storage services, block and file services on an E7-based platform. So it's a very, very interesting use case there, because as you may know, the E7 is a machine check architecture. It's what Intel calls the mainframe killer for its reliability, its price points, and of course its performance. And the great part about that is that we're able to harness that the same way we would any other Intel processor, except that of course that gives us a lot more horsepower to drive storage I/O. So we just sit on an x86-based system, a 3550, a 3650, a 3850, 3950, and are able now to really exploit to the maximum extent possible, and I'll actually put some proof points around this later on, exploit that hardware to now drive tremendous amounts of storage I/O to keep your applications running at peak efficiency. And of course, ultimately keeping your users happy, because that's really what it translates into. At some point, the user interfaces with that application. So now that we've got that set, let's talk a little bit about storage pools. Now, storage pools we could spend probably the rest of the day talking about storage pools, because this is really where the DataCore engine, if you will, what we are is a data abstraction layer, just like Vmware abstracts the compute and allows compute to float freely between various host servers. We do really the same thing, but for your data, because now your data is no longer tightly coupled to the underlying hardware. Now that's very important, because when we talk about storage virtualization, that's really what we mean. Now storage virtualization tends to be a subcomponent of what we are lumping together as calling this the software-defined storage space, right? Because there's other things besides just the data abstraction that come into play with software-defined storage, and you saw many of them on the feature page that we just looked at. But the important thing to note, though, is that when we talk about software-defined storage, well, at the end of the day, if you really think about it, storage or any sort of system at all is really a combination of hardware and software. Now, the software may be in the form of software or firmware or something else, but it has some sort of instruction set that drives that hardware to do something useful. So software-defined storage is kind of funny to us storage people, because it's like, well, yeah, it's always been software-defined, really. It's always been software-driven to some extent. There's been instructions there telling it what to do. So I say, basically, roll that all up. You can't have a pure hardware-only solution, nor can you have a pure-only software solution. You need to have them both. And that's, of course, when you put the two together, then you have something very meaningful. And as you know, the amount of CPU, the amount of capacity on the disks, the type of disks that are available today, all those architectures now are changing very, very rapidly. And DataCore allows you to now have the agility to keep up with that and to be able to introduce any of those technologies when you need to introduce them into the environment. And that introduction, by the way, is in the storage pool. Now, the storage pool, like I said, is the abstraction component. So any disk, any block-level disk, and we consume block, by the way, and we present block out the front to the application server, but we can also consume NAS-based storage. But ultimately, just to keep the conversation simple, we are natively block in our pool. So when you introduce a physical disk device, and that is very, very generic purposely for a reason, because we don't care what the device is, okay? We don't care what manufacturer it is. We don't care how it's connected. We don't care where it's coming from. As long as we can see it, we can leverage it. So, of course, that gives you a tremendous advantage when we're talking about introducing a Lenovo storage solution into an existing environment. Normally what's going to happen is that's going to have to integrate with something else that already is pre-existed in the environment. obviously there's going to be times where it'll be a complete greenfield, but a lot of the majority of the time it's going to be, well, I've got this other system over here I need to integrate and migrate away from. Can you guys link the two together? Well, no problem at all, because we can work with pre-existing stuff as easily as we can with new stuff. So, but in any case, once that physical disk device, whatever that happens to be, is put into the pool, then that now becomes a member of the pool, not only from a capacity perspective, but from a performance perspective. And the reason why I note that here is because that'll be very important when we talk about auto-tiering and the differences between the use of flash in our system as opposed to the caching mechanism, which is a very, very different mechanism than what flash is used for, at least in our environment. So moving up the stack now. So now that we've got some physical disk resource in that system, in that pool, now what we do is we create these objects called virtual disks. And the virtual disk, of course, as you can see above the red boxes here, that is in what we would call the virtualization space. Okay, so everything below those boxes in the pool, that's in our physical space. That's the physical management component. The front end is the virtual presentation component, and that's going to be in the form of virtual disks. Now, the virtual disk is very simple. It's just a well-behaved SCSI LUN, right, like any sort of storage system would present, except that, of course, it's virtual. And also, anything that is written to that is also thinly provisioned automatically in our pool. So it is a very special SCSI LUN, but to the application, it has no idea that it's a virtual disk. It's just simply saying, I'm a SCSI LUN with a certain amount of size. And in this case, we're actually showing what we call a multi-path mirror volume. So even though it's a single virtual disk, it has multiple paths to that particular object through however many front-end target paths you want to deploy in the environment for this particular scenario. Now, once the application server sees that, and by the way, we can present that either over iSCSI, so 1 gig, 10 gig, 40, and 56 gig Mellanox, or over Fiber Channel, which of course, 4, 8, 16, and soon to be 32 and beyond, or you can do it simultaneously, right, depending on the type of applications that you're driving. We can give some over Fiber Channel, some over iSCSI, so you can have a hybrid approach on the front end for various application needs. But once the application server sees that, they simply see, again, a well-behaved SCSI volume, and now you can do what you would normally do to any other disk object. You can present it raw to an application, or you could perhaps, in the case of Vmware, which is very popular, you could format it as a data store, or now with PSP4's release, you could give it over to Vmware and to be used as a Vball member in that particular space, and that's a very powerful capability, especially obviously in VMware environments, where now, if you're familiar with Vballs, the VMware administrator no longer has to worry about the storage components of having to carve out that volume. It simply asks the storage system, hey, I need these different requirements to be met. Give me a volume that meets these various requirements, and the VM administrator no longer has to go down to the storage layer to get anything done. So that's the top to bottom. So the virtual disk pools with physical disk resources, virtual disks that are carved out of that pool, and then the application presentation above. Now, what I just explained to you was the traditional model, right? This is the model that we've all known for years and years and years since storage started. Some sort of back-end disk, some sort of controller, some sort of application that is consuming that storage. So this should be very, very familiar to you. Now, what we've done, and we'll move over to now the right side of the screen. What we do here, and we actually are showing hyperconverged there, but it's really before you can even have a hyperconverged discussion, you have to understand what converged storage is first, right? Because there's one in the middle here. We just consolidated it to make it easy on this graphic. So converged storage is now taking and harnessing the power of, again, today's modern servers, but also now coupled with the fact that today we've got very, very high capacity drives, which means you can have a tremendous amount of capacity, say in a 3650, right, 2U system. You can put as much as 60, 80, 100 terabytes of storage into a 2U system now, and now effectively eliminate the back-end SAN, if you will, eliminate the complexity, eliminate the cost, and most importantly, eliminating the back-end latency to get to the disk, right? Because now we've eliminated all those extra wires and switches and all that stuff to get to the storage. Now it's all inside the server on very, very high-speed circuit pathways without having to go out over all these various wires and translation from electrical to light and then back to electrical again. Cuts down a lot of latency. So all those things are affected. Now, when we move into hyperconverged, all we're saying there is now not only are we moving the storage up from underneath into the server, we're now moving the application down onto the host as well. Now, that's a very, very interesting concept. And of course, that's why hyperconvergence is becoming so popular. Again, the same reasons. Reduces complexity on the front end, reduces cost, but most importantly for us, and we'll demonstrate again in a little bit here what we mean by high performance, is now you've eliminated a lot of the latencies again on the front end and the back end, and that directly translates into application experience and user experience. By doing that, you're actually eliminating orders of magnitude of latency and can drive tremendous amounts of storage I/O for the application. And so it's really a win-win-win-win across the board for the application and the environment. So let me see if there's anything else I want to mention on this slide. Well, we have also cloud storage listed here. I'll just point that out briefly. Again, like I had said earlier, it doesn't matter where the storage is coming from. So we just as easily as we can consume block storage on the back end, we can also consume cloud storage, because one other important aspect to note here is that because we run on an x86 and we require an operating system, we actually run within a Windows kernel. Now, a little bit of information about that, because that probably made some people sit up in their chairs. So a little bit of history here before we go into some of the mechanics of it. So back in 1998, when our company was formed, we actually, interestingly enough, and somewhat ironically, we were founded by Unix engineers. Unix engineers, very, very objective Unix engineers, set out on a mission to really find what was going to be the best operating system to deploy on. Now, today this might not be such of a big deal, but years ago this kind of was a big deal. But those individuals made a decision that Windows has a very, very unique nature. Okay, it's not just what Windows gives us, it's also what it doesn't do, which is get in our way. So that is to say, when we run in a Windows kernel, and that was back then, and it's certainly still true today, Windows is the only commercially available, widely distributed operating system that is what we call deterministic real-time microkernel processing. So to make that very, very simple, deterministic in real time, of course, means that we have to be able to be certain that something is going to get done in a very, very rapid manner, but that it has to complete within a certain time frame in order to be useful to the system. So an example of this would be your airbag system in your car. Okay, the airbag system in your car is a real-time system, and if it wasn't, it would be useless. Very much like a non-real-time based kernel would be useless to us, because if the airbag does not deploy, let's say the airbag deploys 0.1 seconds too late, well, that's the difference between life and death. Okay, so that's a real-time system, very much like our microkernel inside of the Windows NT kernel that we have today. So that's why that was chosen. Now, there's been many attempts to bring a real-time nature to various operating systems out there, which are basically in the form of hacks and modifications. But the problem is, especially with open source-based kernels, every time you make a modification, you have to recompile the entire kernel, and that requires all revalidation and recertification of all of its components because you've made a fundamental change to the engine. Windows has a very special nature in that it has an altitude system. It's meant to be pluggable, which means that we don't have to recompile the kernel every time we go and we update our software, which of course we do like anybody else from time to time, fixing things here, adding new features, and so on. So that makes a very, very extensible use of the operating system. Now, the other part, which is also very interesting, again, ties into performance, because I believe we want to focus on performance and availability for this discussion today, is that just as much as what Windows gives us, and everybody I think understands what I mean by that, it's the most widely deployed operating system, the first operating system that's typically developed for any technology that's going to bolt into a system, a computer system. It's typically developed for Windows first. And of course, it's very widely distributed, so it's very, very common, very popular. Now, at the kernel level, what we're doing is because the nature of the deterministic microkernel, it allows us to do something very, very special. Which, by the way, and I'm not spilling any intellectual property beans here, but this is very, very unique, and this is really at the heart of what when we talk about parallel I/O, this is how we do parallel I/O. So the way that our engine works, our scheduler, or what has been historically called our polar, we have now a system which we've had since day one, but it hasn't been able to be exploited until the hardware advances came about. In fact, it's interesting when you look at the flow of technology, typically software will follow hardware, but in this case, it took years. It took approximately 8 years for the industry to catch up to our software. And what I mean by that is in the form of multi-core processing, right? Massively parallel processing capabilities of these commodity x86-based systems today. So now you take a system that has been developed from the ground floor over 17 years on this what we call a polar model or a non-interrupt scheduler model. We now have the ability, which we've had since day one, to drive I/O through a x86-based system without interrupting the CPU to do it. Now that is extremely unique. I don't know of anybody who's doing it, in fact. It's so unique. Because it's not an easy thing to do, to say the least. It is taking a long time to develop that and tune that and bring it to where it is today to be able to drive the numbers that we drive. But the way it works is, imagine you have a circular train track and you have a high-speed train on it, and it's just going at full speed the whole time. Okay? Our polar, or our scheduler, takes the CPU, and instead of only interrupting the CPU when we need it, we just take control of it and we just run on it. Okay, which means we're just running. We have the full attention of the CPU. There's no need to interrupt it in order to drive I/O. So as that train, that polar, spins around on that track, and we put a payload on the back of it, well, we don't have to slow the train down in order to put the payload on, and we don't need to slow it down to take it off. Right? We just allow the I/O to come in, we move it to the location, and we offload it. And that doesn't slow anything down. So that's how we're able to drive the level of performance that we do, and not actually impact the performance of the system, and of course drive world record performance numbers, which we'll talk about here in a little bit. I have some slides around the parallel I/O and the performance that we've recently done as it relates to the storage performance console, the SPC1, which is really the authority in that space. So just I wanted to touch on that a little bit. Yes, go ahead.
Got a question came up. Says when configuring the storage on local servers, do you rely on the hardware RAID controllers, or do you present disks as JBOD?
Well, we can consume anything, so that's a great question, and that's a very common question that comes up: is what is valid as a disk? So any disk in a JBOD form, in a RAID 5, a RAID 10, a RAID 6, or any other RAID that you can come up with, as long as we can see the disk that's being presented from that RAID controller, we'll consume it, because we don't know that it's rated at the end of the day, right? Because there's a layer of virtualization, if you think about it, happening at that RAID controller level that's masking the true nature of what's behind it. So we actually have customers using all of those different RAIDs behind us in the pool, if you will, because those RAID controllers just present a single or multiple individual virtual disks themselves to us to be consumed in our pool. So anything goes from that perspective. Now, I will say that there are specific times where you may want to consider one RAID level over another, as an example. And again, JBOD is also a use case, and I can give you an example for that as well. So let's take both of those just to drive that home. So when would JBOD be something that you would typically do? Well, the nature of how our pool works is when data is written to the pool, we do it in what we call a storage allocation unit, which by default, unless you change it, is 128 megabytes. It can go as high as 1,024 megabytes, a gigabyte, or it can go as low as 4 megabytes, right, depending on what you're trying to do in the pool. And that's another thing I want to also note, is that each pool can handle up to 8 petabytes of storage, and you can have 1,024 disk pools per node, so you can have 8 exabytes of storage sitting in a single pool. just to show you the level of scalability we're talking about. But in a JBOD scenario, when would that actually be applicable? Well, let's say there's a lot of technologies out there today that have what we call these all-flash arrays, right? And if a customer has that, that can be introduced into our pool. But typically, and I'm not going to say typically, some of the pools or some of the storage arrays, the all-flash arrays today, don't have any software, right? There's no intelligence. They may be just a whole bunch of, cards or flash devices sitting in an array, but it's pretty much just what we call a JBOF, right? Just a bunch of flash as opposed to JBOD. So there's no intelligence there to provide rating. So when you put that into the disk pool, you just simply drop the individual disk objects into the pool, and we're going to stripe across that like we normally would, because we're going to make sure that we also have, again, there's this word parallel again. We're going to maximize the degree of parallelization on all fronts. Right, so this would also include the disk pool. So we're going to make sure that the most number of devices are involved in driving I/O when we have to talk to the pool. So that would be a scenario of a JBOD, and where you don't have RAID capability, and that's perfectly fine because when you put two DataCore nodes together, as you can see on the graphic here, we do something called synchronous mirroring, which will do the protection of the data. By the way, we can also do disk pool mirroring inside the pool. So if you wanted to do a RAID 1 type configuration where there was no RAID capability, you could do that as well in the pool, as well as across the nodes. And we'll talk about the differentiation there in a minute. Now, in the case of a RAID, which is what most people typically do, they'll carve out, if you've got internal disk in this example, let's say you have 12 drives, maybe you put, you create a RAID group out of the first 6 and the second group of 6. Create a RAID 5 or RAID 6 disk from that, and then just present both of those disks to our pool, and we will consume that the same way we would consume a JBOD, right? There's no difference, because we don't know at the end of the day what is ultimately there. But I would say rating technologies, RAID 5, RAID 6, those sorts of things, are certainly good ideas, because at some point there's going to be a disk failure, right? It all depends on what level of resiliency you're trying to go for. I prefer a RAID 5, RAID 6 model because I understand the mechanics of how our pool works, and that is where RAID 5 has traditionally been something that's been viewed as, well, very, very poor performance capabilities is no longer the case in our pool because we have capabilities now at the software level called random write accelerator, which of course random writes are the most heavy operation you can do against a RAID 5 set. We completely eliminate that. And we'll talk a little bit about that when we get to that section on performance. So hopefully that answers your question. Just carve up what would make sense. And by the way, all the models that we already have today with Lenovo takes that into consideration. But it's not written in stone, right? We still have the flexibility there to do just about whatever you would need to do in the environment. But know that we've already taken those things into consideration with the various models that we have established with Lenovo. But great question. Any other questions before I continue? Okay. So let's do this. Since we're talking about, and I'm going to stay on this.
Sorry, Jeff, my phone.
Yeah.
My phone locked up on me. Question just came in. Where is this technology applicable? What type of client/size?
Great question. It's really everywhere, and I can speak at least from our customer base. We have clients that have as small as 1 and 2 nodes in an environment, a couple of terabytes running for their corporate applications, all the way up to multi tens of petabytes across 8, 10, 12, 14 nodes spread across a metro cluster, right, for hospitals. And one of the largest hospitals in the country, in fact, is actually running, has been a customer of ours for over 12 years. It's actually running on Lenovo hardware today up in New York, and they have multi-petabytes of storage sitting behind that, and they actually have a metro cluster. One side of it is on the New York side, one side across the river in the New Jersey side. And they recently, with Hurricane Sandy, had to rely on that in a big way. Now, up to that point, we had saved the day many times before that event, but Hurricane Sandy was a reminder that even in New York, which typically is not viewed as hurricane territory, like South Florida is, where I live, weird things can still happen. And what happened was they knew the storm was coming, and they actually allowed the system. They shut down one side and allowed all their applications to run. I believe it was on the New Jersey side, because the New York data center, I believe, had some flooding. So they were proactive in that sense. But even if it was an event that caused an outage of one side, the application still wouldn't know about it. So to answer your question very directly, really anybody that has data, first of all, that it means something to their business, meaning without their data, their business doesn't exist, which I would say, again, without the data, most companies would suffer. We are very, very, very data-driven society, and so anybody that falls into that category, couple terabytes up to multis, tens of petabytes and beyond, is really someone who can benefit from this technology, because again, we allow an unprecedented level of flexibility with regards to the storage and the configuration of that storage, because that's a pretty serious expense today, and it will continue to be that way because we are in control of so much data. I actually read a Gartner report a couple months ago. I believe it was from last year, but the numbers that they were showing, not just for what the storage that was in place today, just the net new storage that was slated to be introduced in 2015 was a number that I didn't even know what it was. I mean, it was just series of zeros and zeros and zeros and zeros on this line. It was very, very apparent then at that point that we have a major problem of dealing with the sheer amount of data capacity on these systems today. And of course, as all these types of technologies like the Facebooks, the LinkedIn's, all the social media stuff, and not only, but including the banking systems, the financial sectors, right? The hospitals, the healthcare. Everything is digital now. Everything is image-based, right? You get a check in the mail. The first thing you do is you grab your phone, you log into your bank app, and you take a picture of it, and boom, it's instantly deposited into your account. Well, that image has to sit somewhere. So now imagine, hundreds of thousands, or hundreds of millions of people doing that on a daily basis. That adds up tremendously. So we have to get our minds in our technology wrapped around this problem before it gets really out of hand. So that's why these sorts of technologies that give you amazing efficiency are very, very important. Any other questions before we continue?
Yeah, there's two more.
Okay.
There's two more come in. They're sending them to me privately. If they send them to everybody,
and I'll try to be more brief for the sake of time here as well, and we can follow up if we need to.
Does the DataCore software sit on a hypervisor or run in an OS like Windows?
It does. It runs inside of Windows, but it can also run inside of a hypervisor. So we can run directly on the bare metal right on top of Windows. And we'll talk about hyperconvergence more specifically here in a little bit. But you can have your x86-based system, your hard, metal frame, put Windows on there, put DataCore on there. DataCore inserts itself as the storage engine inside the Windows kernel, and now that is, for all intents and purposes, an enterprise-grade storage controller. Of course, the same thing is also true if you run us inside of a VM, because anywhere you can run a Windows operating system, you can run our software, which, interestingly enough, because I have this up here on the screen, you can run us inside of Vmware, KVM, OpenVM, Oracle VM, whatever hypervisor system you have out there. As long as it supports Windows, you can deploy it there. In addition to that, you can deploy us out onto cloud as well, right? Azure, Amazon, VMware's cloud, anywhere that Windows is supported there, you can also have a storage engine deployed there. And typically where that comes into play is when you're doing disaster recovery. You want to have your data sent off-site to a cloud provider, and you can also now diversify across multiple cloud providers, any cloud provider that can run a Windows workload. So that's very, very, very powerful. You said, was there a second question?
There's another. Yes, there is. Is there going to be something similar to VMware vSAN ready nodes for DataCore?
Well, yes. We actually, vSAN today, what we call vSAN, is a specific use case within the hyperconvergence space. So as you can see, hyperconverged here. Hyperconverged can mean two things to us, and again, I just touched on two of them just a moment ago. But typically, what we're talking about there is we're talking about DataCore running generally either next to Hyper-V, right? Because Hyper-V is just an application to us, but it's a very specific application, serving up storage locally on the same box or across the entire cluster to that Hyper-V hypervisor. Or running us inside of a VMware VM and doing the exact same thing, taking over the local disk or any attached disk that node is connected to, and consuming that in our pool, looping it back and presenting it to the host that we're running on, but not only that, but to all the other hosts that are in the cluster as well, to use that local storage on the node as a shared storage device, or in other words, a SAN, if you will, a virtual SAN, across all of the members in that cluster. So yeah, so that when we say vSAN, that's generally what we mean, but vSAN and hyperconvergence are very, very closely related. So when you hear those two terms, they're pretty close. Any other questions?
There's one in the chat. You should be able to see.
Oh, I have to switch. Let me switch my.
Oh, I'm sorry.
That's okay.
So I covered the SMB space from a hardware perspective. What's the minimum number of servers needed to have a cluster, 2, 3, 4, and is there a tool to calculate usable drive space after the system takes over?
Wow, great questions. Okay, so the minimum number of servers needed for a DataCore cluster. One clarification, DataCore does not consider itself a cluster. We consider ourselves a grid, but I know what you mean. So that's a great question. So the minimum that you need in order to have anything usable is actually 1. But what we say when you deploy DataCore, generally you're going to be deploying for high availability. So you're going to have a minimum of 2. And that, of course, comes in stark contrast to many of the solutions out there that require 3 or more in order to pull off what we do with 2. So 2 nodes in a synchronous mirror will give you what we call high availability, and another way we say it typically also to drive the concept home is data in 2 places, because we do a synchronous mirror. So now we've brought a level of high availability to the environment that most organizations don't have unless they're running very, very high-end storage platforms. It's already baked into the product, right? Data in 2 places is what synchronous mirroring does for you. And of course, it adds that level of resiliency beyond just the simple components in the environment. Now, as far as the usable drive space is concerned, that just really comes down to, again, talking about what the configuration is of the server. So I'll give you an example. So let's say we've got a 3650 2U box, and we've got 10 terabytes of storage in each one. Well, if your intention, and this is all done at a virtual disk level, not at a pool level, but at a virtual disk level, and that's very important, because now you may decide to have all of your volumes mirrored, which would then effectively mean that your 10 terabytes in each node becomes 10 terabytes usable because we have to write it in 2 places, okay? But because it's done at a virtual disk level, that level of granularity, you may decide that, well, only these 3 volumes are considered mission critical, and I'm only going to mirror those 3 volumes. And then the other volumes, I'm just going to have single instance copies of them. Maybe they're used for, test dev, or maybe a scratch volume or something like that, where it doesn't warrant having to have a synchronous mirror running underneath for that disk. So that would mean that your effective amount of consumable space would be more than 10 terabytes. It might be closer to, say, 20 terabytes, right? So it just depends on what you're doing. Now, it's also the other side of that answer is understanding that everything that's in our pool is thinly provisioned. So when we ask customers questions around, how much storage do you have, really what we're asking is how much data do you have? Now, some people will say, oh, I just go on my backup, I can tell you exactly, but most will give you a generalized answer. They'll say somewhere in the order of, say, 150 terabytes of actual data. That's the number we're focused on, because that's all our pool cares about. And that's another interesting point I want to point out here with regards to virtual disks. Remember how I told you that the disk pool itself, each individual pool can hold up to 8 petabytes of physical disk? Well, on the front end, on the virtual disk presentation side, because we're thin provisioned, you can present each volume can be up to 1 petabyte in size, and there's no penalty for doing that. So if you have an application that only needs 100 terabytes, then go ahead and carve out a petabyte size volume if you want, because you're not going to be penalized for it, because we only are going to consume on the physical disk in the pool the amount of space that constitutes the data, not the allocated space, not the provisioned space, only the space that is enough to hold the data. And that, of course, is also makes life a lot easier when you go to architect these systems, knowing that you're actually going to get full use of that storage that's in the pool. So while we don't have a calculator per se, if you just simply understand those concepts of whether you're running mirrored or not mirrored, that'll help you get and arrive to the calculation. Of course, the Lenovo, the technical folks at Lenovo have all been trained on this. Certainly, we are available as a resource to come along and assist with that, but the solution architects out in the field will from Lenovo will be able to answer that very, very quickly. That's a very straightforward process for them. So hopefully I got to all of your questions there. Or maybe there was there a last part of that question there, the 3-server Hyper-V cluster? We can certainly do that. Oh, this is a different question, I'm sorry. In vSphere, Hyper-V, VMware Essentials, really popular. What would the licensing be for a 3-server Essential? Okay, so from that perspective, if you want to deploy a DataCore virtual SAN on a 3-node system, you would need 3 DataCore licenses. So this is the difference between hyperconverged and what we call traditional. It's the same product, okay? The only difference is how it's licensed, right? You don't lose anything. It's not a different product or a module or anything like that. It's the same great software, all managed from the same interface, just licensed differently. So the difference, the primary difference, by the way, between hyperconverged and traditional is that hyperconverged, or virtual SAN, you can only serve DataCore virtual disks to other nodes that are running DataCore, okay? Now, it's not that you're serving it to the DataCore node across, from one node to another. From a licensing perspective, there has to be DataCore software on that node in order for it to be a valid member to be able to use that storage, okay? The idea around that is because that's hyperconvergence is driving toward a lower cost model. So, of course, the software has to limit you somewhere to be applicable to that particular use case. And that's how that's done. So, for instance, the flip side of that would be, let's say you had a virtual SAN in your environment and you wanted to present it out to your AIX system or your HPUX system or some other external system outside of that virtual SAN. The software will not allow you to do that. It's only going to allow you to map to other DataCore virtual SAN running nodes. And that could be, again, Hyper-V, it could be Vmware, it doesn't matter. As long as DataCore is on that box, that's a valid member. As opposed to traditional, which traditional licensing, you can go ahead and serve up disk to anything on the planet, right, over any technology you want. On the network, on the fiber channel side, just serve it up to every application that you have out there, and there's no restriction there. So that's the distinction there. Now, also, from a capacity perspective, the hyperconverged licensing is also done on a per node capacity base, and this is maybe a little bit more information than you need to know right now because this stuff is already skewed up in the Lenovo system today. So but just so you know, there's already predefined set amounts of capacity that's been carved out for each license for a hyperconverged system. So that's in the order of, say, 8 terabyte, 16 terabyte, 32 terabyte, and so on, all the way up to a petabyte per node. I'm also going to just throw out a couple other things as far as a distinction, because I'm sure there's a lot of questions around this with regards to what are the differences between DataCore virtual SAN and, say, VMware virtual SAN? Well, first of all, which may be obvious, but I'll say it anyways, the storage that runs in VMware can only be served if you have a VMware system. If you have anything else, you're out of luck, right? So that's the first limitation. Second limitation is that they require flash. There's some sort of flash technology in each one of those nodes. We do not. And hopefully we have time to talk about the differences between flash and how cache is differentiated in our system. So I'll try to talk fast here. And then, of course, there's no rating capability, at least as of the last update I got. They did not support any sort of rated disks. So it had to be all individual disks because of the way that they consume those disks, the physical disks in the nodes. They just don't support rated technology. I could be wrong on that, but I believe that was the last update that was still the case. So from a cost perspective, it's pretty significant, right? You need to have some sort of flash, high-speed disk device, and you need to have more nodes than what we would require in order to have a highly available environment. And then, of course, what we typically say is, why do with 10 nodes what 2 nodes will do for you, right? That's the idea, and we really do show that very, very well with performance. And we already touched on performance, so there's a couple other things I want to point out if we have time, but we'll cross that bridge when we get to it. We have a couple other questions here, or did I have to scroll up here, I think, to see all of them? Let's see. Okay. So what is the cost to license the 3 servers? So the DataCore, I'm presuming you're talking about the DataCore cost. So the Lenovo folks can actually provide all the costing information.
Yeah, sorry, that's what my original question was more of when I asked about the cost of licensing over VMware on a 3-server deployment, right? So, right. And this may be specific to small businesses, but a lot of times it'll be, all right, we had 2 servers that are about to die, and we just want to virtualize. So it's right. Customers looking at doing 3 servers of SAN and VMware licensing, and I'd like to be able to propose DataCore instead of a SAN. So what's it going to look like to license those 3 servers? Not getting into technicality or anything like that. Yeah.
Sure. So again, Lenovo can provide you the Lenovo SKUs and everything around that, but I can tell you in a general sense, if you're talking about, of course, it'll be dependent on capacity, but each node has to have a certain license on it for its own capacity. So in the case of an 8 terabyte license, for instance, MSRP with 3 years of support for that is $6,000, right? So and that would license a single node, and of course, in this case, you use the 3-node configuration, so it would be 3 times that amount. But that would allow you to consume and manage 8 terabytes of physical disk. Okay, not the presentation of the virtual side, right, to the application. That can be anything. It's just right. What we're physically managing inside the box. So MSRP with 3 years of support, $6,000, and then it just goes up incrementally as you approach up to a petabyte. So
that's perfect because it actually puts it into the price range of what a SAN would be. So I mean, if I could populate out 3 servers with X amount of disk, I mean, 90% of the time, what people in SMB are looking for is between when they ask for SANs, between 5 and 20 terabytes usable. That's about it. So
right. Yep. Exactly. And another major distinction as well, and I don't believe this has changed yet with VMware, but I'll throw it out there, and someone can correct me if I'm wrong. We can consume any disk with a virtual SAN. It doesn't just have to be internal disk. It can be externally attached disk on that node as well, right? So I think VMware only consumes internal attached disk, is from what I last read. So again, it's all about flexibility, right? We have a model that the licensing model, the cost model fits this type of deployment model. We want to, not have too many trade-offs, right? We don't want to compromise the real benefit of the software by locking it down too much. So we allow pretty much all the same things that you would do in a traditional model, but in a hyperconverged model. So there's a question here: how does one model IOPS for the implementation for this grid? So a question about IOPS and performance in general. I'm guessing. Anyway, I think it's Christian. Can you elaborate on that, just so I get to the question? Is that okay? So, from an IOPS perspective, and maybe this is a good time perhaps to switch over, because you've been looking at this slide the entire time. Let's switch over to our parallel I/O slide deck, just to show you some brief things here. So, long story short, because this has been a long process as SPC1 tends to be, but we just published. And this will be going public here probably next week, maybe the week after Thanksgiving. It depends on how it flushes out. But we just completed the world's first release of a hyperconverged, software-defined storage, hyperconverged storage performance council benchmark, SPC1 benchmark. It is the de facto standard when it comes to not only just raw performance, but also from a cost performance aspect. So took about, say, six or 7 months or so to perform it. We performed it, by the way, back all the way in 2003 and set the world record then, and this is going to be no different. So this, I'll just jump right to it for the sake of time here. Let me actually go to this slide and go to slide mode so then I can transition through. So this is a typical cost per IOP, SPC1 IOP specifically, because the SPC1 is not an iometer workload. This is an OLTP, very highly transactional, high-intensity workload designed to really find where your storage breaks. Okay, the intention is to push the storage as hard as possible to see what it's capable of.
There's a gray box showing up on the screen.
Oh, that might be. Is it this one? The chat window, maybe? Is that better?
Could be. There you go. Better.
Perfect. Sorry about that, folks. Okay. Thank you for that. So as you can see here, these are all numbers that are available on the SPC1 website. Anyone can go and look at them. And generally what you find, of course, is that you have this trend line. Generally speaking, the more money you spend, the faster the performance of the system typically is. And then, of course, these systems can go anywhere from $50,000 all the way up to multi-millions of dollars. I believe right now the world record holder on performance is a company called Huawei. And I believe they hit the 3 million SPC1 mark with a system that costs somewhere in the order of, I think, $2.4 million if memory serves correctly. So fairly large environment, right? Well, here's the interesting thing. Now, what I'm about to show you is DataCore out of the box today, nothing new, right? This is just DataCore 101. And by the way, this was done on a Lenovo X series server, interestingly enough. And what we did was we destroyed this graph, okay? Now, this was done with a box that was around the $30,000 mark. In fact, I want to say it was a 3550, so it was a one-use system. But the really important aspect of this, and maybe this is a good segue into the performance side because we spent a lot of time on the availability side. Let's talk about performance a little bit more. In that, the ability to harness not only the CPU power, but also in this case the DRAM, which is what we actually consider as cache. Okay, we use the DRAM as cache. So we don't treat Flash as a caching device. We treat DRAM as a caching device. So you now have a very, very highly efficient software harnessing the power of all the CPUs, if necessary. In this case, it certainly was because the SPC1 is designed to push it to its limit. Harnessing all the CPU power, all that multi-core processing power, along with DDR4 RAM, and all the efficiencies that the software brings as far as moving data in and out of the system, right? Remember, we're non-interrupt based, so that's very important to performance. To be able to give you now a system that has that level of impact, what you're seeing on the screen here, we've just invalidated that entire graph now. We are extremely now disruptive in the space. Now, the interesting thing is this is not new, right? We just decided today to do an SPC1, and that's what we were able to produce. Now, what that has done, interestingly enough, has made our engineers, all of our principal programmers or software guys sitting in the lab, to sit back and say, you know what, it's just interesting because we actually have some self-imposed limitations in the software that today with the multi-core processors are no longer necessary. So all I'm going to say is we're not done running SPC1s, and this number here, you will soon forget about the 460 number. Okay, as magnificent as that looks on that graph, that will come and go very quickly because what we have running in the lab now for our next round will dwarf that number considerably. Okay, and what is that related to? Well, not only obviously the harnessing the power of what we have available to us in today's modern architectures inside these powerful Lenovo servers, but also removing some of those limitations that we've imposed on ourselves years ago. Now to take advantage of these multi-core systems, because multi-core systems have only been around for, what, 6, 7, maybe 8 years, if that, right? So it's now making us go back and take all those governors off of the accelerator, right, to allow us to run well beyond NASCAR speeds with, again, the same hardware. So this number is going to go up considerably even more beyond this. By the way, we've already published, and you should start to see these numbers appearing on the SPC1 website. And by the way, the current world record holder right now for the cost performance, which is what this is showing, comes in at about 24 cents per SPC1. We have published 8 cents per SPC1, so 3 times better than the current world record holder on nothing more than just a basic server, essentially. Nothing fancy, nothing special, just using what we have available to us from an internal storage perspective with multi-core processors, and I will say there is a special nature around Lenovo servers in general. As everyone I'm sure is aware, Lenovo has very well documented to be the most reliable server vendor on the planet. And I'm not just saying this because I'm on the phone with a bunch of Lenovo folks. That's a true statement. That's a documented fact. Now, why is that important to talk about performance? Well, the level of quality engineering that goes into a Lenovo server also equates to efficiencies throughout the entire system. So we're able to do some very interesting things with Lenovo servers as it relates to performance that we really can't do with anybody else. And certainly this is really the case when you start moving up into the E7 processor line and the special architectures that they've designed around linking all of their processor books in their 4-way and 8-way, like 3950 type chassis. There's some really, really interesting things there. It's an awful lot of horsepower, and we can take advantage of all of it to drive I/O numbers that the industry hasn't even dreamed of yet. So stay tuned for that. That's coming. So let me flip back over to the questions because we're coming up on about 7 minutes left. Is that correct? I want to stay true to your time limitations.
You have 20. I mean,
20. Oh, 20 minutes. Okay. Oh, that's right. We were on a little bit before that. Okay. Let me see. Make sure I don't miss anything. How much processor resources is used toward getting these IOPS? Okay, that's an excellent question. Now you guys are really driving into the whole parallel I/O discussion. So, and with regards to other resources on the system. So, excellent question. So, while it is true that we can drive on as many processors as you have available to the system, of course, if that's not your intention, in this case, of course, for an SPC1 benchmark, it is the intention to find out where the breaking point is. And that test will do it. But in normal production terms and on normal operational day, that's not going to be the intention, clearly. So you can cap that, right? So what we call the number of polars that are available for the system to spin up. And I actually do have a graph on this too I'd like to show you, because this actually will demonstrate graphically what we're doing. That is a dynamic aspect of our system. So let's say all of a sudden a tremendous amount of demand is now presented to the system. The number of polars will dynamically spin up, and then will spin down once the workload goes away. But what will happen is, and I don't know if this is the right one here. Yeah, didn't really go into that much, but you get the idea. As we start to spin up the workload, the polars will increase, and then the workload diminishes. The polars will give back that CPU. But of course, you can also lock in the maximum amount. So let's say, for instance, you had a dual, like a 10-core system, dual 10-core, 20 cores, or 40 threads of execution, because we also will run on hyper-threading as well. But let's just keep it simple for now. Let's say we have 20 cores available to us. You could say, well, the DataCore system is really, really efficient. It doesn't really, I mean, you don't need to necessarily have even 10 cores, right, driving I/O, because more than likely your workloads that are running on that are not going to even drive that level of performance requirement. But let's go ahead and lock it into where it can't go higher than, say, 8. And that would mean that you have 12 cores now available for any other application that wants to use it. And keep in mind that it's not only applications that sit outside of the DataCore. In the case of hyperconverged, which is what that SPC1 benchmark was showing, and I'll go back to that because that's extremely important to point out. When you look at this, which is right here, okay, when you run traditional SPC1, they have to include the workload generators above it, above the storage, and then the storage cost itself in order to drive that test. We are running the SPC1 workload on the same system that's running the storage engine, okay? So that has a tremendous impact on the on the cost of the system as a whole. But what my point is here is in showing this is that as the number of cores increase, the number of obviously cores available to drive I/O, of course, can also then naturally increase, but you can limit that. And and now you can have applications, which is what we call hyperconvergence in a general sense, or more specifically, co-resident application support. You can now have on your x86 server there, that 3550, 3650 server, you can have DataCore running right next to SQL, right next to Oracle, right next to whatever application you can put there. In addition to that, even if it's a non-Windows-based workload, you can still run it. Run it as a Hyper-V virtual machine, because we'll just serve that storage directly up to all the virtual machine workloads that are sitting right next to us on the same box, right inside the kernel, right? No longer needing to go out over the wire to get to the storage. It's just a kernel call now inside the same system. And you can now drive Linux workloads or any sort of open source workload on that system without having to have that as separate layers. So, and again, controlling how much resource each side takes. But I'll be honest with you, unless you're running a workload like this, you typically, most customers find that you don't need more than, say, 6 to 8 cores to drive it, because our software is so lean that you couldn't generate enough workload to really ramp up the number of polars that you would need in the system. I mean, it just generally is not an issue. You have more processing power available to you in these current architectures than we really know what to do with. And DataCore, because of the way it's architected and designed over all these years, you know, if we're using 4 CPUs, you're probably driving a tremendous amount of I/O just with 4 CPUs. So you won't need to worry about that part. And by the way, out of the box, the default setting, just for the technical folks in the crowd, the default setting for the maximum polars, I believe, is 10. But of course, that can be modified to meet whatever the requirements are on the box. So, yeah, great series of questions here. Let me see if I can get a couple more in here. If there's any, were there any more questions? Okay, I didn't see any. Oh, that's right. I want to touch on one more thing here as we're approaching our time here, which is back on the other slide deck. This one right here. And this is, I'm not going to waste time looking for the slide. There's too many. Let's bring up the feature slide. So there is
gray box.
Yep, got it.
That one. There you go.
So there's a distinction I want to make between again, the cache and the flash and all this stuff, right? So very, very important also on the economic side. Remember, I told you I was gonna really harp on this idea of the economics being impacted, because all these things drive to doing more with less, and this is just another great example here. So let's talk about performance in general, but specifically the flash and cache paradigm. So as you already know, we use the DRAM as cache, and of course in a synchronously mirrored fashion, when you have multiple nodes involved, we will synchronously mirror that cache, right? So it's fully protected, right? We don't do, in a mirrored configuration, we don't do anything without having the data in 2 places, okay? It's very, very important there. Now, with regards to the use of flash in our pool, okay, as a distinguishing point to the RAM and the caching function that happens at the DRAM level, when you put a disk into our pool, we really do not care what it is. In fact, the only thing that matters is it matters to the operator. So when you put in some 10K, some 15K, some nearline disk into a pool, okay, now you know that the relative performance characteristics for all those different devices, you know, obviously 15K is higher performing than 10K, which is higher performing than nearline. So you will be able to set, just by simply right-clicking on the physical disk object in the pool and saying set to tiering level 1, 2, 3, 4, all the way up to 15. We support 15 different tiers per pool. But now, let's say that, you know, in the future here, you want to go ahead and now introduce flash, which I would even argue in this type of architecture isn't even really altogether that much necessary, because of the heavy lifting that the caching algorithms are going to do for you at DRAM. But if you wanted to add flash, there are specific cases or specific workload types that might help you, because keep in mind, even though we have that high-speed cache sitting up front, we still have to destage that data to disk. Okay, so which means that when we destage, the faster the disk is to accept that destaging operation. Generally, overall, the better performing your system will be. But typically, where flash comes in is when you find that your disks are at contention, and you need to be able to offload that quicker than what a typical spinning disk would. So you put the flash in, you put the solid-state disk in general, whatever that happens to be. RAID-connected SSDs or PCIe-based flash or DIMM-connected flash, whatever the new great super Whammy-Dine stuff is tomorrow, put it into the pool, okay? We treat it like any other disk, but now you're going to set that as a Tier 1 device, which tells the system, hey, this is an important performance object. And now when we do auto-tiering, we're going to ensure that the right data is on the right disk at the right time at the right performance level. Okay, and you don't have to worry about that. That's all done for you in real time. That's all done. But what I'm trying to get at here is that with a flash device, because we're not using the flash device as a global caching system, you are able to not only get the performance benefits, but you're also able to get the capacity contribution of that device. Because as you all are aware, these things are expensive typically, right? Especially when you're talking about PCIe-based flash, okay? They're getting very, very large, and they're getting very, very fast, and their price tag, of course, is, in line with that. It tends to be more expensive. So to miss out on one of those characteristics, right, to only get the performance benefit and not the capacity contribution is a shame. We use them both in our pool. You're going to get it because we're going to treat it like any other disk. Now, a couple other major distinctions between flash and DRAM, okay, just to make sure we're all on the same page. Flash, first of all, wears out, okay? It has a shelf life. DRAM has no real operational life, right? The system is going to be well beyond support life before you have any problems with your DRAM, right? There's no wearing aspect to DRAM because of the way it's constructed. The second thing is that the flash is orders and orders of magnitude slower than DRAM, right? DRAM is measured in nanosecond response times, and flash is measured in tens of microseconds, right? In the computer world, that's a significant difference, okay? And that does translate into application latency, by the way. So that's why we prefer DRAM as a cache, and we always have. The third thing, though, which is really important, is that not only is not all flash equal, right? There's various qualities of flash, there's different types of flash, different manufacturers of flash, but all flash suffers from one important thing from a performance perspective, and that is this concept of write amplification, okay? When you take a flash device out of the box and you run a test on it, you're going to get amazing results. Try running that test for the next day or two and see what happens to your performance results, right? It's going to drop through the floor. The reason is because now what you've done is you've effectively written to the entire beginning and end of the device, and now the garbage collection mechanism has to kick in, because now in order to write new data, I have to either move data, zero the data, and then write the data, or just simply zero the data and write the data if it's an unallocated sector of the device. Okay, that additional writing, moving, checking, clearing, all that stuff, that's a write amplification effect. That means that now in order to write, I got to do 2 or 3 extra writes to get the job done. That is major performance impacting, and that's just the way it is. Okay, all flash devices suffer from that. DRAM has no such failure. Okay. So that means that now you can continually and consistently drive tremendous amounts of I/O with cache. Now, a little bit about cache, okay, because we haven't touched on the details and the mechanics of this yet. So when we say cache, what we mean, of course, is our caching algorithm that is running directly against, in concert with the CPU, but directly against the RAM itself, okay? We will typically take, on any given system out of the box, we'll typically take between 60 and 70% of the available RAM as cache. Now, of course, that can also be dialed down in the interface. It's just a little bar you move, and you can scale that upwards and downwards as necessary. So if you've got an application that's running next to us, you obviously want to give your application a little more RAM, you can scale us back and accommodate that. But what's important there is that, and some of the sales folks on the call will appreciate this little saying that I've been saying for years and years. I don't know where I came up with this, but we say at DataCore that cache is king regardless of how you spell it. Okay, so cache is king. Okay, so the more RAM you have, the more cache you have. The more cache you have, the more space you have to keep data up off of the disks, right? To keep the I/O away from the disk, the better your application response time is going to be. Because another saying that has also been said popularly in the storage space over the years is the best I/O is the I/O you didn't have to do. Well, that's effectively what cache is doing. If we can keep as much I/O activity off of the disks behind us, we gain, actually, there's more than just a performance benefit there, by the way. There's also the fact that we're not having to go to the disk as much means that the disks are not getting pounded on as much. They're not getting thrashed as much. They're not being worn down as much, which means now longevity in the environment, which means less drive failures, longer useful life, and so on and so on and so on. So there's actually multiple benefits to the cache. But the more data that we can keep up there, the more we can service directly out of line speed, if you will, directly off the fiber channel or off the 10 gig channel without even having to go to the disk. So that's huge. Now, there's 4 major components. Just going to mention them so you've heard the names, right? When we say cache, there's actually 4 pieces to the cache. One is our write buffering, okay, small amount of memory that's used to act as a speed matching buffer to get the data off the wire so that you can free up the application to continue doing whatever it was doing, right? The next one is a read cache, which we already talked about, right? That's the majority of the cache that's there that's used for staging data up front so that we don't have to go to the disk. The other 2 on the back end, if you will, so those 2 are principally on the application server-facing side. The back 2 caching algorithm functions is read prefetch, right? We're gonna grab blocks that are adjacent to each other in anticipation that you're probably going to ask for those next. So when we go to the disk, if we have to go to the disk, let's just go ahead and grab what makes sense reasonably from the predictive statistical sense, grab what we think you're going to need and put it up in RAM all in one shot, and that also increases performance. And then the last one is write coalescing. Write coalescing basically says if I'm writing data, as the data is coming into cache, if I find that there's adjacent blocks to the disk in cache, instead of sending every I/O to the disk one by one by one, which of course is a slow process, let's go ahead and coalesce them and send them as a single transfer to the back-end disk. So that increases that'll increase the system performance just that alone, putting DataCore in front of any storage device. That will have a tremendous impact on performance. So that's why we say now, cache is king, regardless of how you spell it. The more cache, the better performance. And by the way, today we support, on a per node basis, we support up to 1 terabyte of RAM. I believe the PSP5, don't hold me to this, but I believe the PSP5 roadmap, which is coming, that release will be out in April of next year. We are planning on supporting up to 4 terabytes, which is the maximum physically addressable non-paged pool space for Windows. And we're going to, of course, support the maximum. So now you can have these concepts of what we call mega caches. So tremendous amounts of cache sitting up front. And again, the more cache, the better for your application, because now you don't have, like take an example of VDI, as this one comes up all the time. Now, when you boot one virtual disk, we immediately stage that in cache. So now that means that now let's go ahead and boot 100 virtual machines. They're all booting directly out of RAM, because the majority of that data is it's static and it's already persisted in high-speed cache. So you're no longer having to hit the disk to do that. So that was a very, very quick and dirty high overview of cache. Again, we could spend the whole day talking about all the implications of that, but there's one more I want to touch on so you've heard of it. There's a feature here called Random Write Accelerator. We can actually send the link out as well. I believe we're going to be posting all this stuff so that everybody can get to this. You have to see this to believe it. Random Write Accelerator is just what it says. Random writes are the most intensive in this case, a spinning disk. There's also implications on the flash side too, but mostly on the spinning disk. Especially, and going back to the question of RAID, RAID 5 has the hardest time dealing with this, certainly RAID 5 and RAID 6, but RAID 5 in general has a hard time dealing with random writes because it causes so much armature action to happen on the disk itself. Okay, it causes a lot of seek time to be incurred just to position the armature over the right place on the platter to be able to write the data. So what we've done is we have a very clever mechanism, and this is an example, by the way, and this will be the last thing I touch on. This is an example of how just a little bit of software can have such a massive impact on your environment. I did a test, and we can send the video out for this. I think it's already on our YouTube page, but we'll make sure you get it, where we had an iometer test running, a full 100% random write workload against a RAID 5 set that was consisting of 6 15K drives. Okay, very, very simple setup, all inside of a single server. We ran the test. Then we got exactly what we suspected we would get against the native disk. We got about between 500 and 600 I/O against that disk. Okay. Then, while the test was running, we went and enabled Random Write Accelerator, and within about, I think it was 20 seconds it took for it to enable the feature across the disks that were in the test. But after that, that 500 IOP now became over 100,000 IOs to a RAID 5 disk, a single disk, consisting of 6 drives in a server. Now, what the heck just happened? It's very, very simple, in fact. If you were to go and run the exact same test against those native disks, and you were to instead run a 100% write sequential test, you will get the exact same results. All we're doing is we're eliminating, in software, we're eliminating the need to care about where to put the data. Remember now, the disks are in our pool, so we know exactly what constitutes the geometries of those structures in the pool. So we don't care where the data goes as long as we're just writing to blocks, obviously, that haven't been allocated yet. So we just write the data. When we write the data, we, again, because we're not looking up where it's going, when we have to actually write it, we update a pointer table later on, obviously, so you have the correct data that you're getting to. But because we're doing that, we're essentially eliminating and completely nullifying the seek time associated with that operation. So what we're doing is we're sequentializing those random writes. So now it is, and another name for this is also sequential storage. You'll see that if you have the software in front of you, you'll see both of those depicted there. That's what we're doing. So that's a perfect example of a little efficiency that has a very, very large impact, because now we've essentially turned those spinning disks into flash devices with regards to random writes are concerned. Okay? So that means now RAID 5, RAID 6, where maybe before that wasn't so attractive, now you can start using those technologies very, very widely, and you're now eliminating the penalties that would be typically associated with those types of technologies. In fact, RAID 5, in my mind, has a performance benefit over even RAID 10. And people will say, well, wait a minute, in RAID 5, you got to write parity, you got to do all this stuff, there's extra writes. But the difference is that RAID 5 has a higher degree of parallelism because there's more spindles involved in a single operation as opposed to what RAID 10 would give you. Because with RAID 10, when you write, you're writing to only half the drives, right? When you're reading from all the drives, but you're only writing to half of them. Where with RAID 5, you're reading and writing equally from all the drives in that particular that structure, that virtual disk, if you will. So we like parallel, right? Because the back end of DataCore is parallel, right? All the channels we're going to be using to drive the storage. We're going to use all the available disks to drive the performance. Same thing on the front end. All the available channels in the presentation of those virtual disks that have direct access to all that highly parallel I/O inside the caching mechanism and inside the CPUs, we're parallel on both the front end and on the back end, which is why we have a whole initiative around this parallel I/O storage subsystem discussion, which is in that other deck, which I can share with everybody on the call. So now I think we are probably close to the end here.
We are.
Any more questions that I can touch on, or are we pretty much, I think we're at the end, right? Yeah, I didn't see any other questions come in. So I want to thank everybody for your time. I appreciate, I've been going for about 90 minutes. Hopefully everyone found some interesting things here, and we'll provide all the documentation and all the slides and everything else that I didn't even get a chance to touch on here. We'll provide it all out to the website. I guess it was Kevin, right? Where you have the link to the video. We'll put the links to the documents as well. Is that right?
Yes.
Okay.
We'll put them out there, and you can get them off of our user group website.
Great, great. And by the way, if there's any other questions, you know, I guess that you'll forward it on from the group to me, and we can address those offline. Does that make sense?
Sure. Or you can put your email address out there, and we'll put it in the deck. They can look at them and get it.
I can put it into the chat window, or just put it into the documents.
Whichever way you want to do it.
Okay, I'll throw it out here so you have it, so everyone on the line has it, and then we'll also include it in the slide decks as well. And by the way, we actually have an alias. I'll throw this one out here as well for everybody. We actually have an alias, Lenovo@datacore.com, which can also be used for inquiries, and if there's everything from deal registration to questions about the technology to training opportunities, because we're certifying a lot of people. We have a lot of online resources. We're also doing, we're actually going up, I think, the last November 30th, the last week in November, we're going to be up in Raleigh training, doing some DCIE training up there as well. So our team will be up there that week. But we have a tremendous amount of resources available for study, for certification, and for field, for enabling folks to do field engagements. So that will all be where you would want to use the Lenovo at datacore.com alias. So feel free to as necessary. And thank you, everybody, for your time. I appreciate it.
And thank you, Jeff. This is a very informative meeting, and thank you for coming on and getting it to us.
All right, no problem. My pleasure.
And that concludes today's meeting.
Okay. Thanks, everybody. Have a great, well, I guess today's Thursday, but soon to be great weekend, and we'll talk to you again soon.